Good morning, class. It's 8 o'clock. I think we can start today's lectures. This is the day that the Lord has made. We will rejoice and be glad in it. So today's topic is AC applied to inductors, and if time permits, we will also look at impedance in RLC circuits. We'll start by discussing self-induction. Self-induction. To discuss that, we'll first look at what inductance is. What is inductance? Inductance is a measure of the opposition a circuit element presents to a time-varying current. And this is by Lenz's law. We discussed Lenz's law about a week or two ago. So it's a measure of the opposition, a circuit element. And what is a circuit element? What is an example of a circuit element? A resistor is an example. So it's a measure of the opposition a circuit element presents to a time-varying current. In principle, all circuit elements, including resistors, have some inductance. Although a coil of wire with negligible resistance has only inductance. This coil is called an inductor. Such a coil of wire with negligible resistance is known as an inductor. Let me pick a pointer. Okay, fine. So when an inductor is placed in a circuit with a time-varying current, it exhibits a reverse voltage, or what we call back EMF, in opposition to the changing current. So this changing current through the coil produces a changing magnetic field and flux. Remember, we discussed magnetic field and magnetic flux some time ago. So the changing current through the coil produces a changing magnetic field and flux. And the back EMF is the induced EMF in opposition to this changing flux, magnetic flux. The back EMF, remember the back EMF, and we said it's always opposing the current, opposing the changing flux. So just a moment, let me see if my colleague is in the house. Okay. All right, we go to the next slide. Because the back EMF is induced in the inductor as a result of its own changing magnetic field, this phenomenon is called, or is known as self-induction. It's known as self-induction. So the self-induced EMF for a coil consisting of N loops is given by Faraday's law. We have done this before. If you go back to your lecture notes, you'll see this formula there. It's Faraday's law. And the time rate of change of the total flux through the coil.
How are you?
Talking. Okay. So the time rates of change of the total flux through the coil, this term here, is proportional to the rate of change of the current in the coil. This is the rate of change of current in the coil, delta I over delta T, where I is the current and T is the time. This is because the current produces a magnetic field responsible for the changing flux. Thus, the back EMF is proportional to and oppositely directed to the rate of current change. And this relationship is expressed using the proportionality constant L. So if we say back EMF is proportional to this, so this is the constant of proportionality. L is the and it's known as the inductance of the coil, or they call self-inductance. So we call this equation 1. So the opposition presented to current by an inductor under alternating current conditions depends on the inductance and the voltage frequency. This is expressed quantitatively by the circuit's inductive reactance, denoted by this term, XL, which is given by this equation. XL equals to omega L equals to 2 pi FL. This equation is known as inductive reactance. The SI unit is ohm or Henry per second, where F is the frequency of the driving voltage as before, and omega is 2 pi F, and L is the inductance, like we said earlier. So in this case, like we saw in the case of capacitive reactance, inductive reactance is measured in ohms. It's also measured in ohms. So this formula is what gives us the inductive reactance. If the inductance is known, if the inductance is known and the frequency is known, you can easily calculate the inductive reactance. But if you are asked to find the frequency and you are given the inductive reactance and you are given the inductance, then you can make F the subject of the formula and evaluate the frequency. So take note of that. The inductance is a property of the coil that depends on, number 1, the number of turns in the coil's diameter and length, and the material of the core, if any. So is actually a property of the coil, and it depends on a number of things. The frequency, that's looking at the physical aspect of it. The frequency of the voltage also plays a role. The frequency of the voltage plays a role because the more rapidly the current in the coil changes, the greater the rate of change of its magnetic flux. I repeat, the more rapidly the current in the coil changes, the greater the rate of change of its magnetic flux. I think we saw that when we first discussed magnetic flux. And this implies that a larger self-induced or back or reverse EMF opposes the change in current. So this is covering the topic. So in terms of XL, the inductive reactance, the voltage across an inductor is related to the circuit, to the current and inductive reactance by this formula. So this is the voltage across an inductor. This is the voltage across an inductor. The circuit symbol for an inductor, and these graphs of the voltage across the inductor and the current in the circuit are shown in this diagram. And you can see that the maximum voltage corresponds to zero current. As is when an inductor is connected, when an inductor, this is an inductor, when an inductor is connected to an AC voltage, the maximum voltage corresponds to zero current. Then when the voltage drops to zero, the current is maximum. So you can see that in a purely inductive AC circuit, that is in a circuit with only inductance, the voltage leads the current by 90 degrees or by 1/4 cycle. That is the voltage. This is the voltage. This is the current. So the voltage is leading the current by 90 degrees or by 1/4 of a cycle. This is half a cycle. This is another half cycle in the opposite direction. So this is, when you go this way, this is a full cycle, like I said the other time. So because the phase relationships between current and voltage for purely inductive and purely capacitive circuits are opposites, there is a phrase that may help you remember. There is a phrase that may help you remember the difference. And it's called Eli the Iceman. Eli the Iceman. And what does this mean? Here, this E represents voltage or EMF, and I represents the current. So these three-letter words, Eli, indicates that for inductance, L stands for inductance. For inductance L, the voltage leads the current. See, the voltage comes first, or the EMF is coming first. So it's leading the current. And for this acronym, this means that the current is leading the voltage. This is for capacitance. C stands for capacitance, while L stands for inductance. So probably this will help you to remember. Like if you are asked a question that for inductance, is it the current that leads the voltage, or is it the voltage that leads the current? So if you have these acronyms ready, you'll be able to answer the question in a jiffy, very fast. So there's a question here. It's actually an example. I want you to write it down. Write down this question. A 125 millihenry inductor. I told you the other time, whenever you have a milli or micro, you must evaluate it by the time you are doing your calculations, okay? You have to write out what milli is. And milli stands for 10 raised to the power minus 3. That means when you are doing your calculations, you have to use 125 times 10 raised to the power minus 3 henries. So a 125 millihenry inductor is connected to a 120 volts, 60 hertz source. What are A, the inductive reactance, and B, the RMS current in the circuit? So how do you calculate the inductive reactance? We go back to our formula, our equation. Use this equation to calculate the inductive reactance. And what do you use to calculate your, what's the second question? Let me go back to it. B says the RMS current in the circuit. And which formula should you use to calculate that? This formula. So you make IRMS the subject of the formula, and it becomes VRMS over XL. So you insert the XL that you calculated in A. You are going to get a value for this XL in question A. So when you get the value, you put the value, you use VRMS over XL, and your VRMS is 120 volts. So try that out. And well, as usual, I expect you to send your responses as messages. And during revisions, sometimes next week, or maybe before I end the class, I'll give you the solutions. Let's do it that way. Before the class ends today, I'll give you the solution to this question. But let's go ahead. Let's go on with the lectures. I'll give you 1 minute to write it down. I believe you always come to class with your notebooks. It doesn't matter if the class lecture is online or not. You must always have your lecture notes with you. So I believe everyone has written that. So we go on to the next slide. The next topic we are going to be discussing this morning is impedance, RLC circuits, or what we call alternating currents in the resistance, inductance, and capacitance circuits, in circuits that has these 3 components. So impedance, RLC circuits. The RLC series circuits. In many instances, alternating current circuits include resistance, inductive reactance, and capacitive reactance. In this case, resistors, capacitors, and inductors are combined in one circuit. In all 3, if all 3 components are present, the circuit is known as an RLC circuit or impedance, like I said earlier. RLC circuits or impedance. Impedance is the effective resistance of an electric circuit or component to alternating currents, arising from the combined effects of resistances, capacitive reactances, and inductive reactances. So the symbol is Z. Those days they taught us that it's pronounced Z, but after some time they said it's no longer Z, it's Z. So we go by Z. So suppose an AC circuit consists of a voltage source, a resistor, and a capacitor connected in series. A resistor and a capacitor connected in series as shown here. The phase relationship between the current and the voltage is different for each circuit's elements. So as a result of this a special graphical method is needed to find the overall opposition to the current in the circuit. And this method employs a phase diagram, what we call a phase diagram. Okay. So in the phase diagram shown for this RC circuit, this is called RC circuit. The resistance and reactance in the circuit are endowed with vector-like properties, and their magnitudes represented by arrows called phasors. So we have a series RC circuit. In a series RC circuit, the impedance Z is the phasor sum of the resistance R and the capacitive reactance XC. So this is what we are referring to. This is the impedance. The impedance Z is given by this relationship. Is the phasor sum of the resistance R and the capacity reactance. So this is the formula or the equation for calculating the impedance. And if you know your mathematics very well, you will know that this is correct. Okay. So on a set of XY coordinate axes, the resistance is plotted on the positive x-axis, as you can see. The resistance is plotted on the positive x-axis. We go back to that. This is the resistance plotted on the positive x-axis. That is at 0 degree, because the voltage current phase difference for a resistor is 0. The capacity reactance is plotted along the negative y-axis. We go back there and look at it along the negative y-axis to reflect a phase difference of minus 90 degrees. Because for a capacitor, the voltage lags behind the current by 1/4 of a cycle. By 1/4 of a cycle. So that is how this phase diagram came about. Oops. Okay. The phasor sum is the effective or net opposition to the current. As we can see, the phasor sum is the effective or net opposition to the current, which we call the impedance. Phasors must be added in the same way as vectors, because the effects of the resistor and capacitor are not in phase. So for series as RC circuits, impedance is given as this. We have seen that before. So that's XC. There should be XC here. Let me pick my highlighter. There's an omission here, where XC is the capacitive reactance and R is the resistance. The unit of impedance Z is ohm. Unit is ohm. The generalization of Ohm's law to circuits containing capacitors and inductors along with resistors is given by this equation. Vrms is equal to IRms times Z. That's the product of current and the impedance. So this is the Ohm's law for AC circuits. Ohm's law for AC circuits. So this is another equation you might be needing. You have to calculate a particular whether a particular voltage or current or impedance. So this is the equation for impedance. This is the generalized Ohm's law. The next slide. Here, the inductive reactance is plotted along the positive y-axis in the phase diagram. Okay, we have said that before. This is just a repetition. To reflect phase difference of plus 90 degrees with respect to the resistance. Oh, okay. Remember that a positive phase angle means that the voltage leads the current. Just a moment. Okay, sorry, we are looking at series RL circuits. Series RL circuits. Okay, something was covering it before. Series RL circuits. Here, the inductive reactance is plotted along the positive y-axis in the phase diagram to reflect the phase difference of plus 90 degrees with respect to the resistance. Remember that a positive phase angle means, let me pick my pointer. Remember that a positive phase angle means that the voltage leads the current, as is true for an inductor. So in the case of series RL circuits, we have the impedance being equal to the square root of R squared plus XL squared. Okay, where XL is the inductive reactance and the unit of impedance is ohm. Unit of impedance is still ohm in this case. Still on, okay. Now let's look at series RLC circuits. Series RLC circuits. That's yeah. Series RLC circuits. More generally, an AC circuit may contain all three circuit elements: a resistor, an inductor, and a capacitor, as shown in this diagram. We have looked at the case where we had just a resistor. We had looked at the case where we had just an inductor. We've looked at the case where we had only a capacitor. Now we are looking at the case where we have the three of them combined. The three of them combined. So again, phasor addition must be used to determine the overall circuit impedance. Subtraction is used because the phase difference between XL and XC is 180 degrees. So this is the phase diagram for this kind of circuit arrangement. This is a phase diagram. It's XL, that direction, XC. This is your R. This is the impedance. And this is the formula, okay? Impedance is called square root of R squared plus XL minus XC, all squared, okay? Because XL, this is from here to here is XL minus XC. And tan phi is equal to XL minus XC over R. So this is a series RLC circuit. In a series RLC circuit, the impedance Z is the phasor sum of the resistance R and the total or net reactance XL minus XC. Note that the phasor diagram is drawn for the case of XL greater than XC. Okay, still have a lot of things. So still on series RLC circuits. Just a moment. The phase angle between the source voltage and the current in the circuit and the current in the circuit is the angle between the overall impedance phasor Z and the plus X axis, which is given as this. We just saw that now. So this is the phase angle in series RLC circuits, like we just had, like you saw here. So that's called the phase angle in series RLC circuits. So notice that if XL is greater than XC, the phase angle is positive. We'll go back and look at that. if XL is greater than XC, if XL is greater than XC, what happens? The phase angle is positive phi, and the circuit is said to be inductive. Why? Because the non-resistive part of the impedance, that is the reactance, is dominated by the inductor. And in the other case, if XC is greater, that's the capacitive reactance. So if it is greater than XL, the phase angle is negative. We go back and look at that. If XC is greater than XL, let's see that again in the diagram. If XC here is greater than XL, the phasor angle will be, the phase angle will be negative, and the circuit is said to be capacitive because capacitive reactance dominates over inductive reactance. It's as simple as ABC. It's as simple as ABC. So if XL is greater than XC, the phase angle is positive, and the circuit is said to be inductive. Inductive because this is greater, and this is the inductive, inductive reactance. Okay, but if the capacitive reactance is greater, then it will be negative because the circuit is capacitive. Because capacitive reactance is greater, it dominates. So there is something we call power. Let me move this down. Blocking. Okay, so that's fine. The power dissipated in an RLC circuit is given by P equals to VI cos phi. Well, we'll still look at how we came about this. Let's go on to this. Let's go on to the next slide. Yes, power factor for a series RLC circuit. Power factor for a series RLC circuit. The average RMS power dissipated by a resistor is PRMS equals to I squared RMS times R, the resistance. This RMS power can also be expressed in terms of the RMS current and voltage, but the voltage must be that across the resistor VR. Must be that across the resistor VR. Excuse me. Yeah. Because it is the only dissipative element. So the average power dissipated in a series RLC circuit can be alternatively expressed as this. P average power is equal to IRMS VR. Okay, that's across the resistor. That's voltage across the resistor. Let's look at more things on power factor. Still on power factor for a series RLC circuit. You can see that the voltage across the resistor can be found from a voltage triangle, as you can see, from a voltage triangle that corresponds to the phasor triangle. Let me pick the highlighter, and this is what we are talking about here. That the voltage across the resistor can be found from this phasor, from a voltage triangle that corresponds to a phasor triangle as shown in this diagram. And there's a lot to learn from here. The RMS voltages across the components of a series RLC circuit are given by VR is equal to IRMS times R, and VL is equal to IRMS times L, and VC is equal to IRMS XC, because the current is the same through each. So this phasor diagram, the phasor diagram in A, the phasor triangle, can be converted to B, a voltage triangle. Note that VR is equal to V cos phi. VR here is equal to V cos phi. Both phasor diagrams are drawn for the case of VL greater than VC. VL greater than VC. So the voltage across the resistor is given as this, and the term cos phi, yes, the term cos phi is called the power factor. Cos phi is called the power factor. This cos phi is what is known as the power factor. And from the previous figure, let's go back. From this previous figure, cos phi is equal to R over Z. Cos phi is equal to R over Z. And this is known as the series RLC power factor. Series RLC power factor. This equation is known as series RLC power factor. The average power is rewritten in terms of the power factor. So you can write the average power in terms of the power factor. So evaluating, making R, if you cos phi is, if you make cos phi the subject of the formula, or you evaluate for the power factor, you have this as a series RLC power. Because power is dissipated only in the resistance, so we have the average power equals to I RMS squared times R. So the average power is given as this. If you make R the subject of the formula here, you have Z cos phi. And Z cos phi, if you insert Z cos phi in this equation, you have I RMS squared Z cos phi, giving us the average power. And this is known as, also known as the series RLC power. This equation holds, this equation holds, this equation holds for power factor. So depending on what you are given in your question, you can either use this formula or this. So let's look at this. Note that cos phi varies from a maximum of +1, that is when phi is equal to 0 degrees, to a minimum of 0 when phi is equal to plus or minus 90 degrees. Cos phi is equal to 0 degree. When cos phi is equal to 0 degree, the circuit is said to be completely resistive. That is, there is maximum power dissipation, as though the circuit contained only a resistor, as if it's only a resistor that is in that circuit. So the power factor decreases as the phase angle increases in either direction, because cos minus phi is equal to cos phi. So in other words, as the circuit becomes inductive or capacitive, in other words, as the circuit becomes inductive or capacitive. So at phi equals to plus 90 degrees, the circuit is completely inductive. It's completely inductive. Take note that when phi is equal to 0 degrees, the circuit is completely resistive. But at phi equals to 90 degrees, plus 90 degrees, the circuit is completely inductive. And at phi equals to minus 90 degrees, it is completely capacitive. So in these cases, the circuit contains only an inductor or a capacitor, respectively. So no power is dissipated. In practice, because there is always some resistance, a circuit can never be completely inductive or capacitive. That is, in practice, a circuit can never be completely inductive or capacitive. Okay, so all this we have learned has to be applied through questions. So there's a question here. There's a question here, or I call it an example. A series RLC circuit has a resistance of 25.0 ohms, a capacitance of 50.0 microfarad. Remember what I always tell you. You have microfarad. What does that suggest to you? It suggests 10 raised to power minus 6. So you multiply 50 by 10 raised to power minus 6. And an inductance of 0.300 Henry. If the circuit is driven by 120 volts, 60 hertz source, what are A, the total impedance of the circuit, B, the RMS current in the circuit, and C, the phase angle between the current and the voltage. The phase angle between the current and the voltage. So we will apply all the equations we have seen. The solution has been given here. The individual reactances are calculated as follows. Using this formula, capacitive reactance, we have 1 over 2 pi FC, 2 pi 60 hertz times 5.0 times 10 raised to the power minus 5. Someone is confused. This is very trickish, but it's still the same thing as 50 times 10 raised to the power minus 6. So sometimes your knowledge of these things can be tested, okay? So somebody will look at it and say, oh, she used 5 instead of 50. And it's supposed to be 10 raised to the power minus 6 here. Look at it carefully. 5.0 is different from, oh, I should have picked my pointer. Sorry. So we have 50.0 microfarad. Now we have 5.0 times 10 raised to the power minus 5. It's still the same thing. So this is the answer you get. If you punch your calculators very well, remember 5 to evaluate that. And so they are asking for the total impedance in the circuit. Take note of this, total impedance. Total impedance, that's the question. Total impedance. To know the total impedance, you have to find the capacitive reactance, you have to find the inductive reactance, then you have to impute them here. So the total impedance is given by this equation, and you have been given, let me see, the resistance to be 25 ohms. So when you evaluate that, you should be able to get this as the answer. So it will be there for you to look at later. So the next question, B, is to find the current, RMS current, and using the formula, this formula, VRMS equals to I RMS times Z. You can find what, now you know what Z is from the previous, from A. You impute it there, you find your I RMS. For the phase angle, tan phi, given by this equation, you make tan phi the subject of the formula, and you are supposed to get this, the face angle. So it will be there for you to look at later. I think this brings us to the end of Physics 104 lectures for second semester 2020-21 academic section. Your CA test 2 has not, a date has not been fixed for your CA test 2, but I think it should come up in the week of between 18th and 25th of this month. I think so, but it has not been fixed by the department. You will be informed as soon as a date is fixed for it. But I would like to have one more section with you, probably next week, Monday or Thursday, maybe preferably on Monday, because I've not really been able to look at your messages and your questions. So I will take time to look at your messages, your questions. If you have anything to say, put it down, write it, and send it as messages. So next class, Monday, 8 o'clock, we shall look at some questions. Okay, I promised to give you solutions to that, the questions I gave you earlier. Let me see if I can give you the answer. Yes, the question of 125 millihenry inductor is connected. Let me go back there. Oops. This question, I promised to give you the answer. I don't know if you have sent your, let me see, some of you have. Ma, give us the slides. Ma, we have the slides. We need the slides, Ma. Okay, I'll find out how you can get the slides. I'll find out from Dr. Shakwade. We'll put our heads together. Slido, okay, I've heard you. You need the slides, but I thought you have access to these slides already. I don't know. I'll find out. Don't worry. We still have the whole of next week to interact, but probably maybe on Monday, only Monday. Okay. I've seen your messages. I've seen your messages. Don't worry. We don't, Ma. Okay, you don't have access to it. Oh, really? All right. Is that why your midday and Oshuta, you are raising up their hands? So, well, whatever it is, don't worry. We shall meet again on Monday by the grace of God. And I'll find out from my colleague how you can, whether you are supposed to have access to the slides. But I thought this class is available to, I mean, the slides are already available, but somebody said we don't. Don't worry about that, okay? Now, let me give you the solution to this problem. Let me see what some of you have submitted before I give you the solution. I think we still have a little more time to end today's class. This is 8 minutes to 8 by my time. Let me just go through what you submitted. 47.1 ohms, 2.55 amperes. Yeah, that looks good. Yes, correct. All right, let me see others. Just a moment. I'm looking at your submissions through chats. Yes, Oguniran, yeah, right. Okay. Is it only Oguniran that submitted solution? Oguniran is going to have a bonus mark then. No? Maybe you've not had time to look at it. Bankole today, yes, you are correct. Only Bankole and today submitted the solution to this problem. The rest of you, what are you doing? What are you doing? Okay, we still have some few minutes to end the class. You can still do it and submit it before 8 o'clock. I want to see your response to this problem before 8 o'clock. Though I've told you the answers, I've read out some people's answers, and you have it. So work towards that answer you have, the answers you have. So it's been a good time with you. I wish you the very best in this course. I wish you good success, and I would like to encourage you to read very, very hard. Study very well. Physics is very easy. Did I hear some people say no? Everybody is saying yes, yes, yes. Okay, that's right. So have a blessed day. I wish you the very best in your academics. I'm ending the class here. See you on Monday by the grace of God, hopefully.